So this is the final chapter of the book, and it's material that often is treated, or it's hard to sometimes see the linkage to the previous material. And I'm going to try and do that and sort of look at what we've covered and what we're looking at throughout. So this is vibrations. And we've tended to focus in on undamped free vibration, energy methods we may or may not talk about each year, undamped force vibrations, and viscous damped free vibrations in electrical circuit analogs. Now, in terms of Newton's second law, one of the things I've tried to emphasize is that Newton's second law drives this course. So we've had three different types of cases, one which is kinetics, work energy, momentum, and so kinetics has been force and acceleration, work energy has been force, velocity, and displacement, and momentum has been force, velocity, and time. We haven't done very much with the final form of Newton's second law that we can write, which is mx double dot. So we've changed the acceleration, and with that, we ended up with force, velocity, displacement times problems, force, velocity, time problems, which are momentum, and force and acceleration. But now we're going to look at force and displacement and solve basically for the equation of motion, but not solve the actual problem. All of the other chapters we solve for values. Vibration is periodic motion, and you have free vibration. Motion is maintained by gravitational, elastic storing forces, conservative forces. Force vibration, external, periodic, or intermittent force applied to the system. Both can be damped or undamped. And you've introduced various types of dampers in the system already. So here I'm using an image from Wikipedia. Block is released from a displaced position X. Spring pulls on the block, causing a vibration. And the block will move out of equilibrium when X is equal to 0. And for now, oscillation continues indefinitely. So what will happen is it'll move back and forth, and the solution we'll find will work that way. Acceleration is proportional to displacement. So here I have sort of the force is equal to mass times acceleration x, and I can write out all the terms. I've got force, which is driven by the spring. I have the acceleration of the system, and I'll end up with a governing equation that has this form right here, omega n squared. And omega n is just going to be mx double dot plus kx equals 0, or x double dot plus k over m is equal, and the x is equal to 0. So omega is equal to k over m, and my solution is going to have the form a sine km k over mt plus b cos square root k over mt. And in both of those cases, I have the omega n term. So it's the natural frequency of the system. And I can use another form of this expression, which is x is equal to c sine omega nt. What you've done to solve these problems, not really solve them, you've just set them up for solution, is either have a initial displacement with particle moving at or starting from rest, and solving through for x and y, or v, based on that. X is equal to a sine omega nt, b cos omega nt. Then from that you get, well, b is equal to x naught, because a sine omega nt at time equals 0 is 0, and cos omega nt at time equals 0 is 1. And you can do the same thing on the other term, and you end up with v naught over omega n. So these are standard, and you'll end up with sort of these expressions where you might get other forms if you use x is equal to c sine omega nt plus v. And again, xm is going to be an amplitude term. Phi is just a phase angle or shift, and tau is the period of the rotation. And the important thing in that is really this 2 pi term that you have because of the definition of period. Frequency, natural frequency of the system, is going to be again defined here. Energy methods, vibrations from gravitational spring forces. Forces are conservative. And you again can use conservation terms, and this is not my favorite way to approach these problems. But you know that the displacement is going to be at a constant energy level, where T, the kinetic energy, is 1/2 mv squared. And so here, x dot squared, or V is equal to 1/2 kx squared. So if you put all the terms together, you then can do some fun things like say, well, T plus V equals constant, 1/2 mx double dot, or mx dot squared plus 1/2 kx squared. Do the integral, these terms are going to disappear, and you end up with this expression, and you can say, well, that's the same as before. If you do force vibration, undamped force vibration, that's another section of the course. We've looked at cases where we introduce sort of this oscillation, and so you're going to solve for the problem in two parts. You're going to have a forcing frequency omega naught, and it's going to have an amplitude in terms of that force of F naught. Same approach, you draw out the free body diagram, but now instead of just having this term, you now have a second term, which is the forcing frequency. And so it, again, I should be drawing my axes. And when you draw on the axes, you see that this term is positive, this term is negative, and mx double dot, and you end up with an expression of this form right here. X, you'll have a complementary and particular solution, one which will depend on the natural frequency and one which will depend on the forcing frequency. And you end up with c omega squared sine omega naught t k over m c sine omega naught t plus f naught over m sine omega naught t. Now that leads to kind of an interesting result right here, which is this sort of magnification term. And you can see that, for example, when omega and omega n start to approach each other, you see when omega and omega n approach each other, you risk having significant amplification and the problem becoming undefined. So if you have a solution then for x, for these particular cases, it looks something like this. And again, you're not going to solve these problems. You're just going to write this out and substitute in terms. You'll also should be aware of the magnification factor, which is this 1 over 1 minus omega over n squared. If you introduce damping, it adds in an additional term, and it just makes things a little bit more challenging. And here, x is going to be, or the forces are supplemented by this x dot, the damper. And so force B equals cx dot right here. So that's the damper. You have K, which is a spring, and you have the force F, which is sort of there. And you end up with an expression that looks like this, which is not symmetric and means that your trigonometric solutions don't work anymore. And so the solution form is something like this, where x is equal to E lambda t. And you ended up with forms of the equation where lambda 1, lambda 2 are of this form, straight from the binomial theorem, minus c over 2m plus or minus, depending on the solution, lambda 1, lambda 2, c over 2m's quantity squared minus k over m. And then you sort of looked at the term under the square root. You said, well, if it equals 0, then it becomes a critical damping. And in that case, it's 2m square root km over m. So in the case where it's overdamped, that means that the c is greater than c sub c. You have an equation that looks like this. Critically damped, you have two essentially trivial solutions, and that should be a plus bt in here. E to the minus omega n t. and F, the finely underdamped, where C is less than the critically damped coefficient, you have oscillation that occurs. So these two approaches are going to end up with monotonically decreasing functions. The last one will have oscillations and vibration in its solution. In terms of the damping factor, you can relate it to the natural frequency, omega n, and if you do that, you end up with omega d equals omega n, 1 minus c over c sub. Omega d is equal omega d is equal so you have a damping factor, and the damping factor ends up being omega n 1 minus c over c sub c squared, and that relates to omega d right here, and omega d right here. You also have the period of the damped vibration, which is 2 pi over omega d, which is very similar to tau, which you already calculated, which was 2 pi over omega n. The last thing is the electrical circuit analog. We don't do very much with it other than say, look, you can do some sort of matching between a displacing system, a spring mass damper system, by creating an electric circuit. And if you're very interested, and I kind of encourage you to look at it, there used to be an area that was very popular about 40 years ago, and there was a lot of research with analog computers. And analog computers were kind of interesting because they took this idea that you could solve vibration problems and all sorts of things and come up. So analog computers were interesting because they could do all of these calculations relatively quickly, and certainly at speeds far faster than what were capable at the time. There's a lot here, and what you really have to understand is you never really solve for very much. You solve for forces, limited number of standard solutions, and you have to read the questions carefully. And generally, again, it's always going to be of the form mx double dot. You have to look at undamped free vibration, energy methods, undamped force vibrations, viscous damped free vibrations, and electric circuit analogs. What I really want to pull out of this is we're covering this material very quickly towards the end of the course. And I know that it's a lot to sort of pull in at one time. It is related to what we're doing. It is a standard second law approach, but I know that you really have to just look at it a few times to be comfortable with it. And in terms of really important sections, often it's this, the undamped free vibration and the undamped force vibration. You can also look at viscous damped free vibration. Energy methods, they're fun to sort of look at. They're not useful in a large number of cases. Thank you very much, and we'll talk again.